So first, I want to thank the organizers for giving me this opportunity to talk about my work, and also very much for this invitation. So I'm really happy that I'm after Gori, because my talk is quite complementary to her talk, and because I will talk about stellar dynamics, and my galaxies are mostly relatively local. So it's like a really nice complementary picture. So the work that I'm doing is within a big team. So we have a big dynamics team in Vienna, and you see all of the names of my colleagues here. And so why do we study galaxy dynamics? I don't have to say so much because Gori did a great work already. But when we look at the observed galaxies and in the images of these galaxies, and then we try to get the mass within these galaxies just based on the pictures, then we get a big discrepancy, because Okay, so when you look, for example, for the circular speed and just assume the visible mass that we have, then like you would see a velocity curve which goes like this. But in fact, what we are observing is like this. So it's much higher. And this means that it's very likely that we are missing some dark mass in these galaxies, which we call dark matter. And now there's the fact that most galaxies have a lot of dark components, and we just can't see them. So we can't make nice images of these. And that's why we want to use galaxy dynamics. In fact, in this talk, I will talk about two dark components. So we have dark matter, but also supermassive black holes in these galaxies. And how do we study the dark components? We can still make use of the luminous tracers, because they just follow the dynamical potential of the galaxy, which is made of both dark and luminous components. Like typical tracers are stars, for example, gas, or what Gori was saying, showing a lot. But we can also use discrete tracers, for example, globular clusters and planetary nebulae. And now you could ask me, so, okay, you just tell me we have two different kind of dark components. So how can we disentangle them? And it's actually quite nice, because when you look here at the mass of this galaxy, and here's also the profile, then the supermassive black hole contributes a lot in the center of the galaxy, while dark matter, as we know, contributes in the outer parts. So this means that it's quite kind of okay to disentangle them in this work. So why do we study galaxy dynamics? Because, and especially I'm going to show you orbit superposition, the orbit superposition technique, because we can do and find out a lot of really nice things. So we can study the dark halo and the intrinsic shape of the galaxy, maybe even the intrinsic shape of the dark matter halo. We can do extragalactic archaeology by looking at orbits, and also tag agent metallicity to these, so we can find out how galaxies have formed and what is the accretion history. We can study the center of galaxies, supermassive black holes, and also recently we can start to look at subcomponents and disentangle them and study them in detail isolated. So this is a slide from my colleague, and please don't take this too much granted with like all the red and blue, because this is also always a little bit subjective. Like when you look into stellar dynamical models, there are like four main techniques, which is, for example, the genes modeling, which we have also heard about yesterday. So GEM, for example, and GEM is really nice because it is really, really fast. So you can do a lot of models, like dynamical models for a lot of galaxies in a relatively short time. But then it also comes with caveats, for example, that you have to put really strong assumptions, and usually not all of the data is used. But so like I just said, like things come with pros. Oops. Oh, sorry. Things come with pros and cons. So for example, when I say genes modeling only uses a little bit of amount of the data, because we only use the velocity and velocity dispersion part of the line of sight velocity distribution. Then this also means that we can, for example, easily model galaxies for which only these things are available. So velocity and sigma are relatively easy to measure for galaxies, also at higher redshift, for example. So this means that genes modeling can also be applied for high redshift very nicely. So then there's also like something which is called the analytic distribution function. And I haven't explained to you what the distribution function is, but this essentially is a definition of the structure of the galaxy in the phase space of X position and velocity. And we try to connect the distribution function and the potential of the galaxy to the observables. So like maybe just that you have heard the name. So there's this analytic distribution function. Then we can also use orbit-based models from stellar dynamics and made to measure. And I will not go too much in detail with them, but also the slide is online, so you can have a detailed look later or ask me about this. So I will talk about orbit-based modeling here. And this works such that we are creating assuming a gravitational potential of the galaxy. The gravitational potential is made of the stellar component, dark matter component, supermassive black hole, and anything that you want to have. It's also three-dimensional, so we can like have a few also assumptions, and based on the gravitational potential, then orbits are calculated. So here you see, for example, the orbits are calculated such that they are also integrated within time. And so like here you have the start of the orbit, then the time continues. And this is how you would see the orbit in the end in the sky. And this is how you kind of compare the observations. So here are the observations with the theoretically calculated orbits. Yes, so using this method, because we have the orbit, so we can kind of track down what is the orbital space within this galaxy. It is possible to also understand the dynamical structure of the galaxy in detail. So the method that I'm going to talk a lot about is dynamite. I go really fast about it, but this is a Schwarzschild orbit superposition modeling technique. We are creating this in Vienna, and it's also publicly released. So everyone who's interested to work with this can also easily download it and test it. So I think not a lot of people here have used Schwarzschild modeling. So I want to walk you a little bit through the steps that are needed in order to get these dynamical modeling, and especially also the data, because we're quite diverse here within the data. So you kind of have your galaxy, and I just told you, first we have to assume a gravitational potential. So in this case, for example, the total gravitational potential consists of the stellar potential, the black hole potential, and dark matter. So now we want to know like the dark parts of the potential, and the only thing that we actually see is the stellar potential, but we know that the stars in this galaxy, or also you can assume gas or other tracers, they must follow the total potential of the galaxy. So like one part which comes into this is that we have stellar kinematics. Nowadays, we are really lucky because we have two-dimensional, really nicely and high signal to noise stellar kinematics available. And what I show you here is the central kinematics for this galaxy, but often we also use the large scale kinematics because we also want to get a handle on the dark matter. So you can combine large-scale kinematics and high-resolution small-scale kinematics. Now, we also can quite relatively easily get the stellar potential of the galaxy by modeling the surface brightness structure, like modeling essentially isophotes in the images. And then this is both combined in order to get the black hole mass and the dark matter potential. In total, we have to do this for very many models. So we have to build like 6,000 or so different gravitational potentials and always recreate the stellar orbit libraries for these galaxies. And then we try to find the one which best actually fits the observations. And so this is what I'm showing here for this galaxy, for example, like this is the best fit. So you see here the data, so essentially this data, and it's also symmetrized a bit. Then you see here the Schwarzschild model and the residuals. And you see that the Schwarzschild models can actually reproduce the data extremely well. So Schwarzschild modeling is kind of really time intensive, and that's why people, especially 10 years ago from now, would have said you can only use it on a few galaxies, like maybe 10, 20 or so. But there has been a big effort to actually make Schwarzschild modeling available also for many galaxies. And so far we have also applied it to some local surveys and modeled more than 700 galaxies so far, which was for us really impressive because so when you think about it, like getting the Schwarzschild model done for one galaxy takes about 2 weeks. So it takes really some time. And so now I want to show you some early results of the Atlas 3D survey, which I have been modeling. It consists of almost 260 galaxies, and I will also compare it to some of the observations and models from other surveys. And before I do this, I want to introduce to you the concept of the intrinsic shapes. So when you look at your galaxy in the sky, then this galaxy appears kind of like, especially elliptical galaxies appear really elliptical, and you can't really say what is the actual three-dimensional shape of the galaxy. So we need, like, we can't do this based on images only. So we need either spectroscopy or better dynamical modeling in order to find out what is actually the intrinsic shape of the galaxy. And then we can figure out, is this actually an oblate galaxy? Is it a prolate galaxy or a triaxial galaxy? So the line that you always see here is the rotation. So here, like, the rotation goes along the short axis. Prolate is really interesting because the rotation goes along the long axis. Which is a bit difficult to imagine, but many galaxies like this also exist. And then we also have triaxial shapes. And this has also been looked at in simulations. So what you see here is like the mass range of galaxies, the stellar mass range going from 11 to 12.6. And then you see here essentially the number density for prolate galaxies, so galaxies which go in, which rotate in this way, compared to, for example, galaxies which are oblate. So when you think about like your typical galaxy, most galaxies are quite oblate, but also what you see in this simulation, and we also see this a bit in observations, is that the more massive we go, the higher the fraction of prolate galaxies actually become. So when we think about like our typical elliptical galaxies, then we're more thinking of like 10 to the 11 stellar mass galaxies. So I'm really interested in the Atlas 3D survey, because we see here wealth of different kind of kinematics. So I just told you about the quite typical galaxy. So these are the velocity curves, like two-dimensional velocity fields for these galaxies. So this is kind of your typical galaxy in most of the surveys. So you still see quite some rotation, which is also a bit surprising. These are called fast rotator galaxies. Then we have these prolate galaxies that I just told you about, which are kind of, so you have the long axis and then the galaxy rotates around the long axis. And then we have some really peculiar cases, which are kind of galaxies where you don't have a clear receding or approaching side, but you have different components in these galaxies. So kinematically decoupled cores, which have likely formed from a lot of like a recent merger history in these galaxies, relatively recent merger history. And so I was really interested in these galaxies because I want to see how are the intrinsic shapes comparing to these wells of kinematics. And so I'm showing you here to you some really preliminary results. So you see here like the typical galaxy, prolate galaxies. And so this is about the mass range of Atlas 3D. And what you see immediately is that fast rotator galaxies are much less triaxial, while slow rotators are, like these red ones, are usually really triaxial. And it's kind of nice to see, because this is kind of what we would have expected, because these are also often like really roundish. So it's nice to see that this actually is also the case. And then we also have these really interesting galaxies, and they're actually spreading all over the diagram. So we have some galaxies which are not so triaxial, but we also have some galaxies which are quite triaxial. I do not really find so many really prolate galaxies yet. And here in the gray points, I compared to another survey, and we are still discussing this a lot because like what they found is that they found a lot of oblate galaxies, so like really flat galaxies, which I don't find at all. And also other studies don't find this. So like we have a lot of discussion why this could have happened. Also from Atlas 3D, I can get dark matter fractions for these galaxies. And well, I can't really get dark matter fractions because Gauri was just showing you how complicated it is to get dark matter fractions. And I actually have the opposite problem of her because I have a lot of information in the center of the galaxy, but essentially no information outside, like in the outer parts of the galaxies. So I think in the ideal case, we would kind of combine both methods. And so you see here, I have really large uncertainties for these galaxies, and my galaxies, in my opinion, spread a lot. So in my opinion, I can't at all really constrain the dark matter fractions. But like if you would still make, because we have a relatively big sample, if you would still put relations to this, then for example, also in this study, you see like rising dark matter fractions for higher galaxies. So higher dark matter fractions for higher mass galaxies and lower for lower dark matter fractions, which I think also Gauri got. But yeah, the big uncertainties are kind of a really big problem, and there are different possibilities to tackle this for stellar dynamics. One possibility we saw yesterday in a really nice talk is we can try to get really deep observations of these galaxies, and Sebastian showed this quite nicely yesterday for this galaxy 1277. That was actually did not have any dark matter, but this is one possibility to get maybe better constraints on the uncertainties. Different possibilities is that we are not only looking at stars, but that we combine different tracers. So for example, you see here that the stars are only in the very center of the galaxy. So it usually covers about 2 or 3 effective radii. But we also have like a wealth of information in the outer parts from planetary nebulae, for example, or stars in globular clusters. And globular clusters are like nice tiny points. You can study them in detail, and they would give you a big mystery, but we are treating them kind of as a test particle. A student in Vienna, Tadea Versic, has put her whole PhD on studying the dynamical modeling of globular clusters. And one really nice work, which is submitted and hopefully soon also published, is that she was running dynamical models on globular clusters in the SLUX survey. So these are 12 galaxies, 12 EDGs. And what you see here is that what you see here is that actually here you see like each point is a globular cluster, and then you also see in circles the effective radii. So the outer part is 9 effective radii, and you see that her globular clusters can reach almost 9 effective radii. So with the stellar kinematics, we were in the very center. So, and in her work, she was only using globular clusters. So in the future, it would be nice to also combine this. And this is what she got. So she got kind of really precise. I don't show you dark matter fractions, but only the total mass within 5 effective radius. But you can see that the error bars are really, really small. So it would be nice to directly have a comparison now with the stellar dynamics, but I don't have it. Okay, so then there's another really, really exciting work from Tadea, which is that she was also studying Cen-A. And Cen-A is a really, really close galaxy. It's a really beautiful galaxy also. It is about 4 megaparsecs away from us. You see here like a nice picture. You also see it's quite complicated, but the globular clusters in these galaxies have a really clear rotational signal. So this is kind of how you can imagine a bit like a velocity field. And she can get the globular clusters within 40 kiloparsecs, so reaching like really far out in this galaxy. And what is really interesting about this galaxy is also there are a lot of globular clusters. So this galaxy has almost 2,000 globular clusters. So she has a lot of particles. And she now tried to not only constrain the dark matter in this galaxy, but also the shape of the dark matter halo. And it's really, really difficult. This has so far kind of only been done in the Milky Way, and even there, people are not really getting the same results. So it's really, really cool that what she did here. So the M200 value is really consistent here at about 12.5 solar, 10 to the 12.5 solar masses, and this also agrees very well with simulations. And she also got this flattening factor, which is the triaxial shape of this galaxy. And if you translate it to this, what I showed you before, then we see that this the dark matter halo is quite kind of really prolate and triaxial, but the uncertainties are huge. I still have 5 minutes, so I will skip about this, but we can also essentially apply dynamite on higher redshifts. And we can also do some kind of orbit coloring, so we can take into account age and metallicity, and this way we can also disentangle, for example, the bulge of the galaxy and other components. But I also want to talk a bit about supermassive black holes in this conference. And here I show the relatively famous black hole sigma scaling relation. And based on dynamical modeling, so far we have about 150 robust measurements, which does not sound really a lot, but like one dynamical modeling takes really a lot of time, especially if you want to probe the very center of the galaxy. So for now, we have 150 successful dynamical mass measurements. They will also increase a lot, especially with dynamite being now publicly available and becoming faster. And what we typically talk about when we have a supermassive black hole is something between 10 to the 6 and 10 to the 10 solar masses. But you also see that I have put a lot of colors here in this scaling relation, which means that our measurements come from very different methods. And so whenever I gave a talk about supermassive black holes, it's really important for me to tell the people that we are really looking at a really heterogeneous sample. So like it's different data, it's different methods, it's really heterogeneous. So we always have to be a bit careful with when we talk about the black hole scaling relation, and if we want to do any, if we want to use it for simulations, for example, or if we want to understand it. So in my PhD, I was looking a lot into this inhomogeneity, and I was asking myself, is this problematic? So my main conclusion so far is that it depends on the galaxies you look at. It's a galaxy morphology. So in my PhD, I was looking into early type galaxies. So these are all the measurements that I took. So this took 3 years. So you see like how like long this kind of measurement takes. Green and red are early type galaxies, and blue are late type galaxies. And you see that all of my measurements actually were quite well aligned with the literature values. And if like for this relatively homogeneously measured galaxies, like the same data, the same method, the same person doing the method, etc., then this actually aligns quite well with the literature values. So I was really happy actually, because this means that the inhomogeneity might not be a problem for early type galaxies. For just a few galaxies, it's also possible to use the same, different methods on the same galaxies. And what is typically looked at is gas as tracer versus stars as a tracer. And also you see here quite well that they align quite well. So this line is a 1-to-1 line, and they agree quite well. But this is also mostly on early type galaxies. So recently I'm also looking into late type galaxies, and I seem to see some discrepancy, but this has to be looked into further. But so far this is fine. I was really, really worried in the beginning, but so far I'm quite happy. So also, when we look into dynamical if we look into the scaling relations, we see that this is not a complete census of galaxies, because we're actually missing a lot of different galaxy types. So we, for example, often do not model galaxies within nuclear star cluster. So for example, a galaxy where you see this bulb in the surface brightness, so this rise in the surface brightness. We also usually do not model barred galaxies, because they're extremely complicated to model, and also not less compact galaxies. So recently I've started modeling nuclear star clusters. nuclear star clusters and the supermassive black holes in these nuclear star clusters. And this is actually a really great field because we do not really have any information about the supermassive black hole because it's dark, we can't see anything. But the nuclear star cluster is, you essentially see all of the formation history. You see all of the stars which make up the nuclear star cluster. And it has been found out that essentially in low mass galaxies, the nuclear star cluster has mostly formed in situ, while for large mass, high mass galaxies, it has mostly formed ex situ. And now we can kind of compare this also a little bit with the supermassive black holes and can compare, for example, do we get overmassive black holes if we have a lot of ex situ fraction, like a lot of mergers in the past. So I kind of started this, and like you see here, my FCC 47 galaxy, which actually aligns well with the black hole nuclear star cluster scaling relation, but it's a bit overmassive compared to the other galaxies. But I have also put here the Milky Way and M31 because they're really well, really well measured. And this is also a bit inconclusive so far, but we need way more measurements, and some of my students are currently working on this. I will also skip over this. And the last point that I want to address is that nowadays, finally, we can also do dynamical models of barred galaxies. The problem with barred galaxies is that we don't have a steady gravitational potential, but the potential is changing all the time because we have the bar in the center. In this really recent work from my collaborator, we finally are able to model this galaxy with a bar. And what is really, really nice is that we can also get the pattern speed for this galaxy. So you see this here. So this is a pattern speed. So how fast is a bar rotating in this galaxy? And you see here like different dynamical models. And the best fit was at a rotation at a pattern speed of 20, which is relatively slow rotating for a bar. And my colleague also looked into dark matter, and he found that this galaxy actually has a lot of dark matter in this galaxy, relatively a lot of dark matter in the center of this galaxy. And there are some ideas that if you have a lot of dark matter in your galaxy, this slows down the bar a lot, and we do see this in this galaxy. So kind of I just will end here with saying the future is really bright. I also want to repeat again, Gauri is in my conference focus meeting next year. So we hope that we see a lot of you there next year. And coming back to my conclusions, I wanted to tell you that Dynamite is a really nice tool. You can model a lot of galaxies and find out a lot of information about the structure of galaxies. I can't really model the dark matter fraction in, for example, Atlas 3D galaxies, because you need also the larger extent where actually the dark matter dominates, but they are probably combining different tracers with stellar dynamics is probably a nice avenue for the future. And we can also learn more about different components like bars and nuclear star clusters in these galaxies by disentangling the different components. So I want to thank you very much.